are here, root locus design, chapter 6. We're going to start designing with the root locus. We're going to start saying, okay, what gain do we want for a certain performance criteria? And that is doing design, right? That's saying, okay, I want this performance criteria. How do I design my system to achieve that performance? So, in root locus design, which root locus is the broad tool base that we've built up for understanding our performance based on the closed loop pole locations given different gain values. So that whole suite of tools that we've been developing. So in root locus design, our task is to place the dominant closed loop poles such that the closed loop system, first of all, is stable. So in that last example that we just looked at, like that first performance criterion would say, oh, you got to be over in this region here, right? Your gains should bring you over here so that you're in the left half plane and you're going to be stable. This would be bad. You don't want to be over in the right half plane.
So how far how do you know how far you have to be?
And so that really gets into your other performance criteria. So stable oftentimes is just thought of as being kind of binary, like it's either stable or it's not stable. But there is this metric of like how stable are you, and we usually use the gain margin and the phase margin, which are two quantities that we'll talk about in Control 1 if you take that in the fall. And the idea is that it gives you a way of measuring sort of how stable you are. And that, yeah, so that's a little bit more of an advanced topic. I mean, it's not too bad, but it talks about robustness of your controller. But for now, we can just say, okay, stable, unstable, that's what we're focused on. But then we can get into the other response characteristics. So 2, we want the system to have desirable transient response performance characteristics as well, which we talked about in Chapter 3. So remember, when we go back here, the transient response performance characteristics have to do with like that overshoot and that rise time, that settling time, all that, which as we just saw, our locus in MATLAB helps us to understand using the second order approximation, which we'll be using quite a bit. Great. And 3 has desirable steady state response characteristics. Did you notice that little step response that we did last time was actually... Oh, I closed it. Oh. Figure plot y step. Is that not what I should do? Yeah. Did you notice that this is not going to 1? Okay. So we put our command at 1. That's this unit step command at 1, and it's going to like 0.85. So there's a steady state error there. That's not cool. We don't want that. I mean, it depends on the application. Sometimes it's fine, but that seems like 15% off is pretty significant. So we're probably going to want to deal with that. And when we learn how to deal with that in Chapter 4, we add integrators in, right? If you put an integrator into your controller, then you're going to improve the steady state error situation. So, okay. So that's our... those are our 3 performance criteria that we went through. And several types of controllers can be designed using these techniques. The most basic is gain control, which we'll be doing in a couple lectures, which gives us a single parameter, the loop gain, for controller design. The others we consider here are of 2 main types: the proportional integral derivative, or PID, control type, and the other is the proportional lead lag. The 2 are actually quite similar, but the latter can be implemented with passive circuits, whereas the former require active circuits. So if you're going to do analog circuitry, so oftentimes your sensor gives an analog electrical signal back. It's a typical situation. And usually your actuator is some analog circuit-controlled apparatus, like a motor, for instance, and you want to somehow do logic or build this controller that responds in a certain way to the system's response. And the old school way to do this would be to build an analog electrical circuit. So the two options would be to do a passive analog electric circuit where you have like capacitors, inductors, resistors, but you don't have any external power supplied to that circuit. So you don't have any op amps, for instance. So a proportional lead lag class controller you can implement using that sort of circuitry. If you're okay using an op amp with external power, then you can do a true PID controller, which actually is requires that active element like the op amp. So those are our options. So that used to be a significant concern in terms of, okay, which way do you want to go, passive versus active, and PID versus lead lag. Nowadays, most controllers are implemented digitally. So it's not as big of a concern because you're going to have a computer on there no matter what you do. And so PID versus lead lag, it's interesting to do both. We'll look at both types of designs. We'll spend a little bit more time focusing on PID because it's a little bit more commonly referred to, commonly discussed, although they're essentially the same idea, both of them. Yeah, any questions about what we're doing in this chapter? This is the payoff, the last chapter. Okay.
If controls, will we build actual controllers, like physical ones, or is it?
Yeah, so I would like there to be a project where you guys actually implement a controller on a piece of hardware. So yeah, because in a lot of your senior design projects, you need to use a controller, and so you need to know how to build one. So yeah, we'll make them. I'm trying to decide if I should do it with the MyRios that we have in there, which are pretty easy to program, just using LabVIEW, which is pretty nice. But you could also do it with like Arduino controllers, which are cheap and fun. I mean, and they're actually pretty easy to control too. I mean, they're easy to use too. Performance is not nearly as good as the MyRios, though, the LabVIEW-based ones, because those MyRios are expensive pieces of hardware. They have like FPGAs on board, and they do really high sample rates, input-output, whereas the most of the Arduinos don't. There are some new Arduinos that have FPGAs in there, but they're expensive too. So, kind of sucks.
Will you code the MyRios not using LabVIEW?
Yeah. So if you take the embedded systems course, embedded controls course in the spring, that has C-based programming of the MyRios. So we use C, which is the common standard embedded computing language. So yeah.